Thank you, Kent, and thanks everyone for being here. So as Kent already said, I'm going to give you now a short introduction into LabOne Q, which is our software framework for scalable quantum computing. So essentially the top level of our quantum computing control stack. I'm going to give a quick introduction into some of the main ideas and concepts behind LabOne Q. And then in the second part of this talk, I'm actually going to do a live demo. I'm going to show you how you can use LabOne Q to run an experiment that you've generated in Qiskit. Specifically, I'm going to look at randomized benchmarking from Qiskit executed through LabOne Q. And I'm actually very happy that I can follow Niklas here in this talk, because you've already now seen a very good example of what you can do with LabOne Q, much more advanced than what I will show here. I will show a very small aspect of what you've seen has been happening at WMI. They're using LabOne Q as the backend to our instruments. So what is LabOne Q? What are the ideas behind LabOne Q? So with LabOne Q, we're trying to give you more power to focus actually on what you want to do in your lab, designing and running your experiments. So with LabOne Q, we're offering a Python domain-specific language that allows you to program your experiment on the pulse level. So in the way how you're thinking about the quantum computing experiments, that you're executing pulses on your qubits, that is also the way how you program these experiments in LabOne Q. LabOne Q abstracts away from the details of the control setup, so you don't have to think anymore about actually what exact physical output of your instrument you want to play a signal on, but you actually have to think about qubits, logical signals, so signals that you want to play pulses on. And we want to make it easy for you to get started with LabOne Q, so we provide quite extensive examples online. And the demo I'm going to show later is actually based on one of these examples that is available now on GitHub that you can look at. So one idea of LabOne Q is that because we abstract away from the details of the setup, you can treat even complex control system setups as a single machine. And we have a kind of a separation of concern. At the moment when you program the LabOne Q, you only have to worry about the design of your pulse sequences of your experiment. And you don't have to worry about details about synchronization of your setup or about which exact physical channel, output channel you want to play your signals on. That also makes it, of course, very easy to take experiment that you have designed once, migrate them to different setups, larger setups, migrate them to larger experiments, etc., etc. In this way, we offer you a unified and also future-proof access to our control systems, to our quantum computing control system, with this high-level Python domain-specific language. And if you're not yet a LabOne Q user, but at this moment maybe use one of our lower-level APIs like Toolkit, this is actually included in the LabOne Q framework. So the Toolkit low-level API that gives you direct access to all of the instrument properties can also be accessed through the LabOne Q framework directly in the DSL. And last but not least, LabOne Q is released as an open source package under the Apache license. And this gives you the opportunities, even if you have commercial ambitions with your control system software, to include LabOne Q as the backend to our instruments. That is all possible for you. And you can see the source code online. Everything is open on GitHub. So let's get a little bit more concrete. Let's look at an experiment. So here we have a Ramsey experiment. So we have a pion 2 pulse, followed by a delay, followed by another pion 2 pulse, and finally a measurement. How would I do this in LabOne Q in my domain-specific Python language? First of all, I would play a pulse, the pion 2 pulse, on a signal line, which is in this case the drive line of a qubit. So this is the qubit, or this is the signal line that drives the qubit. Then I can add a delay on the same line with a specific time of the delay, and apply another pulse on the same line again. All of this I will package in something we call a section. A section is a timing construct that allows you to ensure that the timing of all your pulses in your experiment are actually exactly as you designed them. So you can think of a section as, if you know about Qiskit barriers, you can think of a section as two barriers at the start and at the end. So a section has an extent in time that is terminated by the barriers at the start and the end, but it also has an extent in the space of logical signal lines. So any logical signal line that is contained within the section kind of defines a second dimension of this section. And if we're now looking at the full experiment that you've defined based on these sections, essentially what you're doing is you're taking these sections and you're playing Tetris on a grid of logical signal lines. And that ensures the exact timing of all the sections one after the other as you design it in your DSL. So now in this Ramsey example, we follow the excitation part where we play the drive pulses on the qubit with a measurement section, which we are instructing LabOne Q to schedule after the excitation section. And here we're playing a measurement pulse on the measure line of our qubit. And then because this is a Ramsey experiment, I actually want to sweep this delay. So this is now a variable that I want to vary in different shots of the experiment. So I add a sweep on the external part of these experimental sections, where I now have this parameter, which is a time sweep, essentially an array of values of time that I have specified in my delay. And that is the meat of how you would write a Ramsey experiment in LabOne Q. Now, when you've designed this on your computer in Python, you can actually now verify very easily using some of the components of LabOne Q that what you have written in your DSL is actually what you want. So you can verify the output that would be expected on the outputs of your instrument, but also the timing of all of these sections and pulses that you have specified in the DSL. For this, we have tools like the output simulator. So here we can take the experiment that you have written and simulate the expected output without having to have any connection to the instrument. This is purely happening on my computer, and this is also what I'm going to show later. I'm not going to be connected to any instruments with my demo, where I now see the expected output on the output channels of the instruments for a Ramsey experiment in this case. So what do I see here? I actually see 3 different graphs. I see an output channel. This is the drive channel of my qubit. And here I see the Ramsey sequence. I have 2 drag pulses where I sweep the delay between these drag pulses. On the second channel, this is the measurement channel where I play the measurement pulse to measure the state of the qubit. Here I have a flat top Gaussian pulse that is always scheduled directly following the second of the pi on 2 pulses here. And the final line are actually the integration weights that you use on the instrument to discriminate between the 0 and 1 state of the qubit in this case. Again, these are actually terminated at the same time as the measure pulse. Internally, there's, however, a delay due to the signal runtime essentially through the instruments. The other tool that you can use to debug your experiments is what we call the pulse sheet viewer. So in the pulse sheet viewer, you actually see the relative timing of all the sections and pulses that you have written in your DSL. This is a very nice tool also for large-scale experiments where you have many, many signal lines to look at, again, the relative timing of all the different parts of the experiment. In this case, again, I see a Ramsey experiment, and I see here, for example, the signal lines, acquisition, so the integration weights, the measure pulse, the drive line. I see the pulses here, and I see the sections in the top part where I have the qubit excitation section and the measure section following it. Again, we're going to see some live examples later of this. With LabOne Q, it's also very easy to access advanced functionality of the instruments. For example, talking about active qubit reset. So we're doing real-time feedback of the qubit state back to the drive pulse. So we select, based on the qubit state we've measured, we select either doing nothing if we find the qubit in the ground state, or we do a pi pulse on the qubit to return it into the ground state. In LabOne Q, you would start this with a match statement. You would match a measurement, which is specified by this ID, a measurement handle. So you have to have a preceding measurement, which tells LabOne Q that this measurement result is identified by a certain handle, which is this qubit state handle. And then I can do match case in Python. So I match this handle to the different cases. For example, case 0, I find the qubit in the ground state, I don't do anything. Case 1, I find the qubit in the excited state, I play a pi pice on the drive line X180. And that would do active, real-time, active feedback, active reset of the qubit state. So one of the goals that I've stated at the start of LabOne Q is that we optimize the lab throughput. We let you do what you want to do most. You want to do experiments. You want to design the experiments. So one other tool that LabOne Q offers, and I already kind of demonstrated this, is this offline and online workflow separation. So what I just shown is to design your experiments on your computer. You do not need to have any connection to the instrument. You do not need to sit in the lab at this point. You can debug the experiments using the tools that I've just shown, the output simulator, the pulse sheet viewer. Can be sure that what you're finally sending to the instrument is actually what you have designed. And then when you're actually ready to send the experiment to the instrument, only then do you need to connect to the instrument and execute on the instrument themselves, on the setup themselves. What is going to come very soon is kind of a next level on top of this. So we call pipelining and queuing. We're going to use a multi-stage queuing, essentially multi-stage queuing capabilities. So on one hand, we're going to introduce a queuing system on the instruments themselves, where essentially multiple sets of sequencer instructions, waveforms, et cetera, can all be uploaded to the instrument in a queuing mode to optimally use the resources of the instruments and the time. And on top of that, LabOne Q is going to offer what we call the job manager, essentially a queuing system that supports a multi-user environment where multiple users can use the same setup. You just submit your jobs, your experiments to a queue, and they're executed once the instruments are free, the setup is not used anymore, and the results are returned to you. All right. I'm already through with the quick introduction, so I'm going to go to the demo. So I'm going to show you randomized benchmarking with Qiskit. And essentially what I want to show here is that we have an interface towards OpenQASM. Qiskit is one of the high-level quantum computing frameworks that can produce OpenQASM. We then, LabOne Q, consume the OpenQASM code produced by Qiskit to produce an experiment from LabOne on the LabOne Q level. If you're familiar with Qiskit, then you know what a backend is in Qiskit. A backend essentially specifies all the parameters of your setup. So what we're here assuming is that the backend, what would be a backend in Qiskit, is specified already. You have already specified your backend in LabOne Q. So you've calibrated your setup, you've calibrated all your qubit frequencies, all your pulse lengths, all your pulse amplitudes already, and you have this information available at the time that I'll show this demo. And now we're coming in. We take a Qiskit quantum circuit, we convert it into OpenQASM, and we import this OpenQASM code into LabOne Q to generate the LabOne Q experiment to execute on the instruments. So let's get going. Here I have Python notebook. This, as I said, is essentially based on one of the publicly available Python notebooks that is on GitHub at this point. It's a little bit more complex than that, but very close. So I'm starting with some Python imports. I'm not going to show this. First step I'm going to do is, I told you, I'm assuming you have a calibrated setup. So you've already calibrated all your qubits. So you've calibrated them, you've saved the data from the calibration somewhere. Now I'm importing this data and I'm connecting to an offline session. I'm running this in emulation mode, so I'm not going to be connected to any instruments here. So now I've imported all this data. And now I can show you, for example, one of these abstraction levels that we have in LabOne Q are the qubits. So qubits are essentially in LabOne Q, they are a container for the signal lines you're using to address a specific qubit for specific purposes. So each of these signal lines then has a name, which essentially encodes the purpose of this line, plus the parameters for the qubit operations, things like pulse lengths, pulse amplitudes, frequencies of any of the lines. All of these can be put into these qubit containers. So this is how a qubit in LabOne Q look like. We have these some qubits, like predefined qubit classes, in this case a transmon class, which has these signals and these parameters. And I'm going to use some of these parameters in the following. Now I'm using these qubits to define a backend. So backend in this case then are the definitions of all the pulses and gates that I want to play on my QASM circuit or in my Qiskit experiment. In this case here, I'm doing a drive pulse. This is a general drive pulse that takes some parameters from the qubit, things like the pulse length or the pulse amplitude. Then I have a virtual Z rotation. So this is simply an increment of the phase of an oscillator that is running on the instruments. A measurement, where I do play a measurement pulse and acquire the signal, demodulate it with some integration weights, and do a discrimination based on the result of this integration. And a controlled X gate. So the controlled X gate that we're using here is essentially, again, copied from Qiskit. So this is one of the cross-resonance implementations that IBM favors. So it has pulses on both qubits, both on the drive lines, and flux detuning for all of the units, for both qubits involved in the 2-qubit gate. All right, so now I have all the ingredients ready to actually go to Qiskit. So now I have defined this backend from my calibrated qubits. So I go to Qiskit, and I define randomized benchmarking circuits. I'll show this here for 1-qubit and 2-qubit, because it's simpler to see first on the 1-qubit, but it is Qiskit. It's all very well defined. So we can look at 1-qubit randomized benchmarking circuit for 16 Cliffords in this case. So we have 17 of these because we have the recovery gate. Now here in terms of the Clifford still, of course, the same is true for the 2-qubit gates. Next, what we would do is we would not use Qiskit machinery again to transpile these abstract Clifford circuits into our basis set that we have defined above. So here we have identity gate, a rotation around X, half a pi rotation around X, a half pi rotation around X, virtual Z gate, and the controlled X gate. These are our basis set. And this takes a little bit. Now we have one of these circuits now in the basis set, no longer with the abstract Clifford notation. You still see where the Cliffords were based on these barriers that we have here. And then we take these circuits, again, still using all Qiskit machinery to transform this into OpenQASM. An OpenQASM program looks something like this. It's always started with an OpenQASM header, definition of the classical and quantum bits, and then it's a sequence of gates acting on the qubits. All right, so now we can use this to define a LabOne Q experiment. One thing is still missing. We actually need to tell LabOne Q how to translate all of these Qiskit statements, so the names of the qubits and the names of the gates, into the names of the gates that we have defined within LabOne Q. This happens in what we call the gate store and the qubit map. So here I define a qubit map where I say, okay, this Q of 0, which is a Qiskit or OpenQASM notation, actually corresponds to my Q0, which is a qubit object in LabOne Q. And here in this gate store, I now register these X gates and the virtual Z and the measure gate for each of these qubits that I have defined in the qubit map. And then I generate an experiment from the QASM using the qubit mapping and the gate mapping as a resource of the import. And now I have a LabOne Q experiment that I can compile and execute, in this case virtually execute, by looking at the simulated output. So this will be the simulated output for a 16 Clifford single qubit RB, just looking at the drive line of one of our SHF-SG instruments. Again, I can look at that circuit in terms of the basis gates. That is not that instructive in this case. All right, another thing I can do, I showed you the pulse sheet. So I can generate this pulse sheet. This actually, by default, generates an HTML document, which I can open in my browser. Again, 1-qubit RB is not that interesting because I don't have any, I only have drive pulses. I only have pulses on a single signal line of a single instrument. So I have a sequence of pulses followed by the measurement, which consists of a readout pulse and an integration kernel. All right, let's do the same with 2-qubit RB. It looks basically like in terms of LabOne Q, the workflow is very similar. I just now have 2 qubits that I have to map to. And of course, I also have to map my 2-qubit gates. In this case, I have to map this controlled X gate, both for target and control configurations with Q1 and with Q0 and Q1. Other than that, it is the same as before. I generate an experiment for my QASM, I compile it, and I can look at the expected output. Here now I have much more lines. I have the flux lines for each of the 2-qubit gates. I will have flux detuning acting on each of the transbands. And I have the drive lines for both of the qubits. Again, this is a 16 Clifford 2-qubit RB. In this case, of course, this is much longer because the 2-qubit RB, 2-qubit Cliffords decompose into much more single qubit gates. And I think I need to increase the length here to also see the measure pulse. I also see the measure pulse, and here I see actually a measure pulse. This is multiplex measurement on both qubits. And I see the pulse output as it would be output on the instrument's output channel. Okay, so I have, I think, a couple of minutes left. So I want to do something a little bit more advanced. I want to take this Qiskit circuit for 2-qubit RB, and I want to tack some active reset on the front. So in Qiskit, this is very simple. I take one of these circuits. Here now, just for simplicity, I take a very short one. This is just 4 2-qubit Cliffords. And then using the Qiskit machinery, I put some active reset gates at the front. So in Qiskit, these are just represented by these projection operators onto the ground state of the qubit. So I now have them at the front of the circuit. I take this circuit, I again export it into QASM. I have to do a little bit of string magic here, which is due to the fact that Qiskit for some reason changes the notation when I add reset gates. So my qubits are suddenly called differently. But now I have the same kind of QASM program. Again, I have the header, I have definition of classical and quantum bits, and then I start with the reset gates that you've seen before. The rest is the same as what we saw before. And now, of course, I also have to define this reset operation, this reset gate, in my gate store. And for this, I'm using what you've also seen in the presentation. I'm using these match case statements for state 1, state 0, and state 1 of the qubit. I have to extend the gate store by this reset gate for each of the qubits. And then I do the same as before. I import the QASM program into a LabOne Q experiment. I compile the experiment, and I simulate the output. Now, this is a much shorter Clifford sequence, but we see we have a bunch of flux pulses, a bunch of drive pulses on both qubit lines. And now if we look at the measurement, we actually have a measurement before the execution of the circuit. This is for the reset. And we have another measurement following the circuit, which was already present before. All right. This is all I wanted to show. Happy for questions.